Hi, good afternoon. Today we'll look at equivalence relation first, then we'll talk about the partial orderings. All right. So let's recall what we have discussed very quickly to point out some important things in connection with equivalence relation. All right. So by definition, equivalence relation is a reflexive, symmetric, and transitive relation. So among these three properties, these two are fundamental for the property itself. So it's really for the concept itself. These two things are very basic things. A reflexive means we talk about equivalence. When we talk about equivalence, then an element will be equivalent to itself. So that's why we need the reflexiveness. And otherwise, the concept of equivalence does not make sense, right? If one is not equivalent to oneself, then the concept itself does not really make sense. So this is really very fundamental reflexiveness. So it's trivial, all right? So for the sake of the concept itself, we need reflexiveness. Then symmetric, this property is really foundation when we talk about two different objects are equivalent. So they must be symmetric. Because usually when we say that two things are equivalent, we say X and Y has some property. So typically we say X and Y. The phrase we are using actually represents a symmetry. X and Y will be same as Y and X. So these two things, Y and X. So when we use and to describe a property, typically it means the relation between X and Y is symmetric. Otherwise, we will say maybe from X to Y. Something like this, then it may not be symmetric. Okay, so these two things are very fundamental for the concept of equivalence. Okay, now the reason for the transitivity is allow us to extend the notion of the equivalence between two different objects or one single object to other objects. So allow us to extend this this concept. Otherwise, it only works for two different objects. It's not that useful. So in order to make it very useful, we want to extend it. So here we talk about, this one talk about connection between two objects. Now we want to extend it to other objects, to extend it, all right? So when we try to extend it, we need consistency. So transitivity ensures consistency. When we say that Y are equivalent, Y and Z are equivalent. So by notion of equivalence, then X and Z should be equivalent. So when R is the equivalence relation, so it has this transitivity property. So that's the reason we need the transitivity. It's allowed to extend the concept in a consistent way. So that's the reason that equivalence relation should have these three properties. Okay. So I hope you have a much better clear picture of why we need equivalence relation and what is underlying it. Okay. Right. Now, yesterday we mentioned the notion of equivalence relation actually is equivalent to partition of set because equivalence relation will define equivalence classes. And these two concepts actually same concept, but we just use different language to describe the same situation. So let me give a maybe a simple example to illustrate why they're equivalent. Okay. So these two concepts, really same thing actually, but use different language. So from equivalence relation, we have equivalence classes. All right. So after each equivalence class is a subset in the partition. So partition will partition the set into different parts, disjoint parts. All right. So each will correspond to equivalence class. What that means is from equivalence relation, we can obtain a partition of the set. So when we talk about relation on a set, so this set S. Okay. So equivalence relation on S will give a partition of S, which is defined by equivalence classes. Equivalence classes. On the other hand, give a partition of a set, we can always define the relation based on this partition, and this relation turned out to be an equivalence relation. So from a partition, we can always define the equivalence relation such that x and y are related if only if x, y belong to same set or some i. So here is S1, S2, S3, S4, S5, maybe S6. Okay. So there they have this one-to-one correspondence. For example, on the following situation. All right. So here I have 5 different regions. So maybe label them with R1, R2, R3, R4. All right. Now set will be union of them. So set as maybe union of these 5 regions. All right. So this one, these 5 regions are partition of S. Now what I can do is define relation based on this one. So such that x 2 points, xy points, okay, xy points, either on the plane, say points. They're related if only if they belong to same region. Now for this relation, it's easy to see it's the equivalence relation. For any single point, of course, it's in the same region. For 2 different points, if x, y are same region, of course, y, x is in the same region. For 3 points, another one, obviously it's transitive. So this one gives us the equivalence relation. Okay. So one thing I want to emphasize again is the notion of equivalence relation is really the same concept of partition, but in 2 different ways. Later on, when we discuss the graphs, next week and the week after, we'll see how we use equivalence relation. Right? Okay, so I think I will finish equivalence relation here, and then we get into partial orders. Sometimes people say partial ordering or ing, with or without it, all the way. Okay. So very often in practice, when we talk about sets, we want to compare elements in the set. Very often we want to compare elements. Say one is less than or equal to 3. The set 1, 2, 4 is contained is a subset of 1, 2, 3, 4, 5, 6. Okay. Or maybe Alice, maybe sorry, just maybe better Bob. Bob is taller than Alice. All right. Or maybe we one have to stop first. Okay. So here again, you talk about ordering in terms of time. One have to do this first and the other thing. All right. All these things talk about making comparison between elements. Different things. So here is just as it's a number, so the magnitude of number. Here is a set in terms of inclusion. So this one is something about this one. So here in terms of their height. All right. So this one in terms of time. But very often we talk about relations that has to do with something that compare certain quality as a quantity of two elements. So in order to formalize this, we will call a relation we add these concepts, the comparison element, and then use the abstract notion into a relation, then we'll be able to talk about ordering of elements. Therefore, we can compare them. So the notion of partial order is exactly try to catch the concept, the abstract concept. It defines how we compare elements. So that's the purpose of partial ordering. All right. Okay. Now, since we just discussed equivalence relation, we can borrow some idea from that definition to see how we can define a partial ordering in order to capture the idea behind this with how we compare elements. All right. So in order to compare two elements, one very important property is what? In order to compare two elements, A and B, I'm sorry. In order to compare them, we cannot have this situation. So if A is smaller than B, B is smaller than A, then what will give us is A equal B typically, right? That's our intuition. So in order to compare two elements, so we should not have this situation. So that means the relation should be antisymmetric. So that's the foundation, fundamental concept when we talk about the comparison. So it must be antisymmetric. Otherwise, we cannot compare them. So they're symmetric, they should be equal, right? So the relation should be antisymmetric. So that's a basic idea behind it, a fundamental idea behind it. Right? So we cannot have this one. So for any pair of elements, if they're related, it only goes one direction, from A to B or from B to A, but not both ways. Okay? So another thing is what? If we borrow an idea from equivalence relation, we have the transitivity that enables us to extend the notion between two elements to many elements. Similarly, antisymmetric only allows us to compare two elements. In order to extend it further, what we need. So if we have x, y, z, so we know x is related to y is related to z. What can we say about the relation between x and z in terms of comparison? If x is taller than y is taller than z, we should say x is taller than z. We should do x before y, and we should do y before z, then we should do x before z. So what it means is transitivity. So that gives us transitivity. So antisymmetric and the transitivity. So relation has to be transitive. Again, that's for consistency reason or to extend the idea. Suppose All right. So in order to talk about the comparison among elements, the relation has to be antisymmetric and transitive. All right. So in equivalence relation, we need symmetry and transitivity. So here, what we need is antisymmetric and transitive. So relation needs to be both. Now, for technical reason, it's best to add reflexive. It's not essential. So this one actually is not essential. But it's useful technically, just for technical reason, because we have a less than relation between numbers. So that was certainly not reflexive, say 2 less than 3, 3 less than 5. This relation is not reflexive. Okay. But in practice, it's more convenient to define the relation to be reflexive. So, but then the problem, of course, with this one, then it's not partial order. So actually, it is describe an ordering. So in this case, it's better that we add these reflexive things. So actually make this relation more look like this one. Then it's a partial order. So that's just a technical reason. Many results for this part applies when it's less than, not only less than or equal. Because this one is not really essential. Okay, so these two things are essential. All right. So with that, we define the partial order to be a relation that is reflexive and symmetric and transitive. Yeah. So I use short form, partial order. Partial order, so such a relation is called a partial order. So that's try to capture our intuition of how we compare with elements with respect to their certain quantity of the elements. All right. Okay. So there are many, many examples. Let's see. In the notes, I give quite a few examples of how to order. For example, less than equal relation on real numbers, integers, say positive integers, and say rational numbers, for example. This one is how to order. And set inclusion on a collection of subsets. Typically, of course, will be a power set of S. Typically, will be on power set of S, for example. All right. Also, the relation that's divisible, this relation say on integers. Say natural numbers, maybe make it easier on natural numbers. Maybe positive integers. I don't want to include 0. Okay. The positive integers. Okay. So that when we write A divides B, so A divides B. So that relation is a partial order. It's easy to see it's reflexive, okay? And it's antisymmetric. If A divides B and B divides A, of course, A should be equal. If 3 divides 9, then 9 certainly cannot divide 3. So if both A divides B, B divides A, then they must be equal. And transitivity, of course, is quite easy. A divides B, B divides C, then implies A divides C. So it's a partial order. All right. Of course, in a partial order, some elements cannot be compared. For example, in with respect to this one, say 3 and 4, they cannot be compared. Because 3 does not divide 4 and 4 does not divide 3. So there may be cases that two elements cannot be compared. That's why we have named partial order. If all elements can be compared, what we get is called a total order. Or linear order. All right, if all elements compared. So for partial order, two elements are comparable. Maybe by A. The two elements are comparable if we either have A or B or B A. Otherwise, they're not compatible. Otherwise, they're not compatible. Right? Otherwise, they're not compatible. So it's called incompatible. So a partial order is a total order if every pair of elements are compatible. There's no incompatible pair. So from ordering a linear order among these three, actually only the first one. So this one is a total order. This one is a total order or linear order. So that means we can add elements in a line. Just we can add element people by their height. So that's called linear order. But these two are not. Because here for inclusion, okay, so for example, 1, 2. So I show some of it. So you see that we can compare the 1, 2 with 1, 2, 3, 1, 3 with 1, 2, 3, or 3 with this one. But we cannot compare 2 with 3 with respect to this set inclusion. Neither can we compare 1, 2 with 1, 3, because neither is contained in another. All right. Okay. Yeah, the actually partial order contain a lot of things, a lot of materials. It takes at least 1 week, 3 lectures, I think, to discuss these things. Even in the textbook, there are too many. So for just 1 lecture, I can only emphasize some important concepts. So I can only emphasize these kind of important concepts, give you basic ideas, and then we'll ask you to read the textbook by yourself. So it's more like a hint to you. All right, these important concepts. Most part of the textbook for that section is easy to understand. It's not difficult at all. All right. Look, in university, it's quite different from high school. In high school, maybe teacher teaches these things, so that's it. In the university, it is not. I teach you only a little bit. Then you have to use these things to study these things by yourself. Because eventually, you have to learn these things by yourself. You cannot always have a teacher nearby you, right? Eventually, you have to learn these things by yourself. The ability to learn things by yourself is very important. And extremely important actually in your life. Not only for these technical things, for other things as well. All right. So for this part, I can only cover the most important things, which I think, of course, it's my own understanding. I think these things are essential, very important. So with these things, you will be able to study other things and learn other things. All right. So that's the basic concept about partial order and the total order, and these and some examples in connection with them. There are another two important concepts, or one important concept is called the minimal or maximal elements. I will give you one theorem. So we have a partial order relation on the set S. Once we have it, typically we will say that set S is partially ordered. S. So once we have this situation, we say that S is partially ordered. Of course, with respect to this particular relation. All right. In this case, typically we say that S is a poset. So we have a term called a poset. So it's from partially ordered set. Partially ordered set. Partially ordered set is called a poset. Okay. So with respect to this relation, very often in a notation, we just very often use this notation. If it's understood what we mean by this particular relation, we use this notation to denote that this set is a poset. The reason is very obvious because this less than or equal to relation is very most common relation when we order elements. So that's why we use this notation. Very often you will not see SR, but instead say S just less than or equal to notation. Sometimes a little bit different. Instead of this one, it's written a little bit different. Sometimes just use this symbol. All right. So we denote this as a poset. The set itself is a poset, means the set has a relation that is a partial order. Is a partial order. All right. Now once we have a poset, once we have a poset, we can talk about the minimal element and maximal element. So these are symmetric. One is minimal, one is maximal. Look here is not minimum, not maximum. So don't confuse it with that. It's called a minimal, here is maximal, not minimum and or maximal. There's another concept called the greatest element and the least element. That's corresponding to minimum and the maximum element in a total order, which I don't want to touch it. In the textbook, there's the greatest element, least element, upper bound, lower bound, greatest lower bound, greatest upper bound, greatest least upper bound, and greatest least bound and least upper bound, and so on. These notions. I don't want to confuse you. So I try to avoid these terminologies, just introduce two terms, minimal element and maximal element. All right. So intuitively, you can feel it, what we mean by minimal and maximal element. So let's take a look at one example, then you will see what we mean. Okay, so maybe the set including relation. So that's a power set of S. We consider the set containment relation. All right, so just for three elements. So suppose S equals 1, 2, 3. So that's our possible subset of it. All right. So there will be 8 of them. Seems to be too many, but it's okay. So there are 8 sets, subsets. And don't forget the intersect. All right. So in terms of this relation, we can see, I just draw a few, I will not draw all the relation, it's too many. So just draw some. This one is so-called Hayes diagram, which I will not uh, discuss in detail at all. Okay, so it's called Hayes diagram. And you can read it in the textbook. It's easy to understand. All right. Now, from this one, in this case, actually, there are maximal element. I found it's actually greatest element and the least element. So what we mean by minimum element? All right. So that means there are no element of y such that y are x. So if y are x, if y related to x, then x must be equal y itself. Now you see the reflexiveness helps. We can write in this way, then x equals y in the definition. Otherwise, I would say no y such that y related to x. So if we think about total ordering, for example, the ordering people with respect to their height, so minimal element is shortest further, right? And maximum, of course, the opposite. That's the tallest further. So in this picture, this one is minimal, this one is maximal. So in this case, there are one minimum element and one maximal element. Now suppose I don't have this subset. So this subset is gone. All right, now minimal element is still same. This one, but maximal element, there will be 3. This one is maximal, this one is maximal, this one is maximal. Now, if I also don't have this one, then the bottom 3 are minimal elements. So this one is, these 3 are minimal. These are maximal. All right, so it's very easy to understand. Now, for total ordering, there are only one element that's minimal and maximal. These are called least. Sorry, I thought I said I tried to avoid these terms. But for total order, anyway, for total ordering, there are a unique element that's minimal, a unique element that's maximal. So these two elements, one is called the least element, another one is called the greatest element. Okay, so that concept of minimal and maximum element. Now, not every poset has a minimal or maximal element. So it's not true that every poset has a minimal or maximum element. So consider all positive integers with respect to this relation. Of course, we see that one is minimal element. One is minimal, but it has no maximal element. Now, if we change this one into all integers, then it cannot have minimal or maximal element. No minimal, no maximal. All right. Now for real number, if I change to even positive real number, positive real number, it has no minimal elements and no maximal elements. Okay. However, we can show, so that's one proof I give to you. We can show that if a set is finite, then it always has a minimal and a maximal element. So that's the theorem I'm going to prove. Maybe best to say, it's better to say things this way. Any final concept contains every finite process contains a minimal element and a maximal element. I will prove that fact. All right. Actually, proof is not difficult. Actually, it's very easy. Okay. So what I do is perhaps it's easier to use this notion. Actually, there are two things. All things will be used very often when we discuss graph theory. One is related to so-called paths in graph theory. So paths, notion of paths. But here we don't use the idea of called a chain. But a chain. A chain is just a relation. Sorry, a chain of elements. So x1, x2, in notes, maybe I will use y. Let me say, actually, my proof a little bit different from that one. Okay, I'll use si maybe. Fine. The description of the proof will be different from what's in the notes. So x1, x2, s3, sk. That it is called a chain if s1 related to s2, s2 related to s3, and so on. Okay, and so on. This is called a chain. All right. Now all SI are different, so they are different ones. All right. So once we have a chain, we can talk about length of the chain. Length of the chain. So length of chain natural way is the number of elements involved or number of these arrows. Do not matter, just one thing. The number of arrows or number of elements. Typically, when we talk about path, will be number of arrows. The number of arrows involved, perhaps number of arrows. All right. Okay. So what we need is the notion of length of chain and length of chain. So there's a number of elements involved, a number of arrows. This is different by one, does not matter. What is important, they're finite. Okay. Now the proof goes like this. All right. So what we do is consider chain on S with maximum length. That's very important. Our maximum here is not maximal. It's we talk about length, so it's maximum length. The chain, this chain is as long as possible. All right, so we have such a chain. So then we see what happens. So we have a chain of maximum length. Say S1, keep on going, keep on going. So as long as possible, eventually, so maybe here is SK. And the length of this one is maximized. All right, it's our maximum length. Now let's take a look. Now consider this one. Let's see. Okay, you lay the theorem of space. Let's see which one. I want to prove max. Let's prove maximal. Minimum is similar. Okay. Otherwise, I will use S1. So let's prove maximal. Minimum, I use S1. So therefore, I use to prove maximal. Okay. So if we don't if SK is not related to any other things, then SK is the maximum element. Then we are done, right? Definition of maximum elements. If we don't have arrow goes out, if we don't have arrow goes out from SK, then SK is the maximum element. Then we are done. We finish. The only thing that prevents SK to be a maximum element is there another element, SK less than or equal to S. So then SK is not a maximum element. Okay? So if that's the J, if so it must go out, otherwise we are done. SK is a maximum element. So otherwise, it goes out. So it goes out to S star. All right. Now the point is, S is finite. All right. Now this one is our maximum length. This one is our maximum length. So that means this S star must be somewhere inside here. So if this goes out, this one must be somewhere inside. So that implies S star equals or some. Okay. So we must have this situation if xk is not a maximal element. All right, now so what? So that's the situation we have. So what? So we have this one as right somewhere in the middle. Now the beauty is transitivity comes in. Transitivity comes into play. By transitivity, what happens? So we can ignore this part. All right. Now by transitivity, what can we infer? So this one related to the x related to this one, so that give us this arrow. So now this one and this one will give us this one. And keep on going, eventually what we get this. So between sk minus 1 and sk, we have arrow in both directions. That's a contradiction to the anti-symmetric. And anti-symmetricness of relation contradicts. So we get a contradiction. So therefore, we cannot have this situation. So therefore, SK we don't have any arrow goes outside SK. So it implies SK must be a maximum element. So we cannot have this situation. So this one will not happen at all. So the whole thing we cannot happen. So you can say it's a proof by contradiction. So therefore, whole set always have a maximum element. Similarly, we can show that it always has a minimal element. All right, so this one is very useful when we discuss topological sorting, when we discuss graph theory or algorithm in the future. All right, I think I will stop here. One thing I want to mention is for the tutorial tomorrow, actually we will not have tutorial tomorrow. Rather, I will postpone it to next week. Talk about solution to homework 4. So next week, Thursday, I think it's a communication day, but for online things does not matter. Tutor will talk about that one, and the tutorial will be recorded. So it does not matter. I think it's better to discuss solution next week. We don't have anything particular to discuss for tutors. All right? Okay? So thank you. See you next Monday. And we will discuss graph theory. All right? Okay? Yeah, MetaMark, I haven't checked with TA yet. I will let you know once I check with TA, okay? Because in the morning I'm reading something related to today's lecture. Haven't had a chance. Yeah, I told them supposed to give you midterm marks today. So check with them.